See how we're going? Well, it's the second part of the unit. So last week we talked about how electrons can jump up and jump down between levels. And today we're going to learn about electron configurations and how electrons fill, how electrons fill in an atom. Okay, you probably learned about electron levels in previous classes, how there are levels of electrons, and the levels hold electrons, maybe? No? Okay, anyway. So, there are levels. Now realize, once again, as my caveat, for those of you who are going to be taking junior level chemistry in college, you're going to learn that this is really not what's going on. This is not the modern model. We're going to talk about electrons as though they are little bits of energy, like they are things that can move between levels. Okay? In reality, well, as far as we know, our technology is getting better and better, and we're learning more about electrons, and they don't really act like things at all. They act more like phenomena. But we're going to pretend they are things. So these electrons can exist in levels. We talked about how they can jump between levels. They can be at level 1 or level 2, and they take in energy and they jump over. And they come back down and they give off that energy. Remember, that's why I had a blue and a green and a red LED. So the blue LED, the photons from a blue LED carried how much more or less than a red LED? More, okay? And we talked about how all stars are what color? Oh, did we talk about the stars? Oh, okay. So, of the colors that I have up here, just a quick review from last time. Of the colors that I have, red and green and blue and violet, which photons would have the most energy? Violet, okay, and it does. You basically say it does follow the what we call the continuum or the visible spectrum. So violet has more energy per photon, and red has less energy per photon. So this comes from a quantum jump. So maybe the quantum jump that would produce a red would basically be 5 units long. So maybe you went from level 1 to level 2 and then back to level 1 and it only gave off 5 units of energy. Remember this? And the violet would be, maybe violet was like 30 units of energy, where it jumped from 1 to 4, then back to 1, giving off 30 units of energy. Okay. I think I mentioned this in the 5th period, but I didn't mention it to you guys, so I'm just going to go ahead and mention it now. This idea that blue has more energy than red, and blue flames are hotter than yellow or red flames, has been borrowed by earth science teachers to basically trick you, and earth science textbooks to trick you, and they say a blue star is hotter than a red star. Here's the problem. While it is true that blue stars carry more energy than red stars, all stars are white. They're all white. Yeah, they're what's called black body emitters. They emit all wavelengths of light. So
we call them blue stars because the wavelength that we see is blue stars.
Because they borrow the idea that blue has more energy than red. So they borrowed this idea, since blue photons carry more energy per photon than a red photon. They borrowed this idea when they wrote their textbooks, and they said, we'll make the hot stars blue and the cold stars red. In reality, all stars are white. They're all white. Our sun is white.
Hi, Mom. Our sun is white.
Mm-hmm. Yeah. Isn't that cool? In fact, when your kids live on Mars and they look up at a nice sunny day, guess what color the sun's going to be?
White.
White. Because the atmosphere of Mars isn't thick enough to cause the bluish light to diffract. And that's why the sky is blue and the sun looks yellow. Because the blue light diffracts throughout the atmosphere.
Where does this blue light go?
So the moon looks like orange or red because as it travels closer and closer to the atmosphere, it has to go through more thick air. So when it's really high, it has to go through less thick air. So it looks the blue scatters and the yellow gets kind of let through. Okay. So white minus blue equals yellow. And then as it gets lower and lower, it has to go through more air. I know. And then it turns yellow or red. Okay. And you weren't going to do anything today. Okay. Is you weren't going to do anything. Now you have a question. Okay.
Yeah. Okay, but if we have like kids living on Mars, wouldn't the atmosphere grow thicker?
If we had that technology, yeah. If we came up with terraforming technology, wouldn't that be great? So yeah, it would be really great to give Mars an atmosphere. But one thing you don't realize, and they don't tell you, is you still could not go, even if we terraformed Mars and had an atmosphere, you still could not go outside without protection because there's no what we call a magnetosphere.
I mean, it's I don't want to go outside.
Okay, yeah.
So on Mars, the sky is
I'm sorry?
on Mars, the sky is
White. The sky is colorless, and the sun would be white. Yep. Okay. Okay, back to work. So we talked about that. Now today we're talking about those levels, and specifically we're going to talk about how much energy those levels can hold. Now a small level, okay guys, back to work. A small level closer to the nucleus is going to have less energy than a larger level further from the nucleus. Okay. Just like when you're running track, if we were to line up all the students in the track, we can get more students on the outside of the track than the inside of the track. Like I said. All right, so the first level can only hold 2 electrons. This was a model. I'm going to make a new one because not even.
That's a pretty bad model.
I know. Now. You're hurting my feelings. Okay. The second shell can hold 8 electrons. Yeah, I thought you did. Thought this would look familiar once we got into it.
What's the model called? I can't remember the model. Bohr model.
It's the Bohr model, sometimes also called the KLM model. But yeah, the basic Bohr model means there's these shells, and you learn it in biology or earth science. Today we're going to take that idea and we're going to extend it one level. Okay, so the first shell can hold 2 electrons, the second shell can hold 8. Follow the little green dot to the periodic table and you'll find that at the top of the periodic table in the first row there's only 2 electrons, hydrogen and helium. That's it. There's only 2. And it turns out that hydrogen and helium have electrons that fill up the first level. That's why we place them at the top of the periodic table. Sometimes you see helium placed over beryllium, for reasons we'll talk about next unit. Yeah?
Okay, so how many elements are in like a line on the periodic table that's like how many electrons can be in that shell?
Yes, exactly right. And it's either 2, 8, 18, or 32. And that is the crux of what we're talking about today. So level 2, you find lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. How many elements occupy level 2? 8. Okay? So it's no coincidence that level 2 can hold 8 electrons, and you find 1, 2, 3, 4, 5, 6, 7, 8 electrons, or 8 atoms. Okay, so far so good? Now here's where this little analogy breaks down. Level 3 does not have 8. 1, 2, 3, 4, 5, 6, 7, 8. Turns out level 3 has 18. And we're going to learn why there's only 3 elements in row 3. Or sorry, there's only 8 elements in row 3, but there are 18 electrons in row or block 3 or level 3. Now the fourth level, and all levels after that, have, well, let's figure it out. This rectangle is 1, 2 atoms thick. This rectangle is 1, 2, 3, 4, 5, 6 atoms thick. This rectangle is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atoms thick. 2 plus 6 is what? 8. 2 plus 6 plus 10 is how much? 18. And this rectangle over here, we're going to call the rare earths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 is 14 wide. What is 2 plus 6 plus 10 plus 14? 32. Guess how many electrons fill in every level after 4? 32. So, sorry, every level after 3. So 4, 5, 6, and 7 hold 32 electrons, as far as our technology allows us to determine. Again, you can always move up. There's clipboards if you want to take your notes and move up. If you can't see the back. Moving on up. Moving on up. Okay, now within these shells, we find orbitals. Now, the International Space Station is in an orbit. The moon is in an orbit. The satellites that allow you to send text to people in Guatemala are in orbit. And these orbits map out a shape. Some of the orbits are a ring. Some are actually a sphere, a ring that basically gets multiplied over itself. But those shapes are called orbitals. When an electron occupies a shape and travels around the nucleus, it forms an orbital, the shape in which it travels. Now, each orbital has a level of energy associated with it. And the amount of energy it has determines what electrons can be in that orbital and how much energy those electrons will have. The lowest energy orbital is the simplest shape in the known universe. What's the simplest shape in the known universe? Yeah, a circle. And in 3 dimensions we call it a sphere. So the simplest shape in the known universe is a sphere, which is why all planets, all stars are spheres. Spheres. Yeah, stars are spheres too.
A star was a square.
I forgot.
Oh, it's okay. You've all said stupid things at one point too. Yeah.
Is there any chance that we could find like a planet or something that's not a sphere, is like more like a geometric shape?
Yes, but that planet would not be able to orbit a star. So if we found an irregularly shaped planet, that planet would be very strange because it would not be orbiting any stars. And that would be really tough to find. But it is conceivable that we could find a planet not orbiting a star. Or we could find a planet that just ran into another planet and it was like an egg shape. But most likely all planets are going to be spheres. Sounds good. Okay. Most asteroids are spheres too. Okay. So each shape can hold 2 electrons. Each shape can hold 2 electrons. Okay? And we're going to find out later on that when they do hold 2 electrons, they are going to be what's called spin paired. We'll talk about that in a little bit. So the simplest shape is the S. So S for sphere, maybe. Some properties of the S: it's spherical. And there is only one type of S. So my sphere, if I had a perfect sphere, like a, well, if it was perfect. If I rotate it in the x-axis, whoop, it's still a sphere. If I rotate it in the y-axis, shoop, it's still a sphere. If I rotate it in the x-axis, or the z-axis, shoop, it's still a sphere. So whether I move it this way, or this way, or this way, it's still a sphere. Okay, so spheres, they're simple and there's only one shape. So since there is only one shape, you can only put 2 electrons in any S. So we say S2. You've seen this, right? X, Y, Z.
No.
Oh, normally the Z is coming out at you, but in this textbook, the Z was going up. So in the Cartesian plane, you have the x-axis, you have the y-axis, and you have the z-axis. So the x-axis, the y-axis, and the z-axis. So you've mostly been drawing everything on the x-y axis.
Now it's 3D.
Yeah, in 3 dimensions, there's a z-axis too.
That's
3 dimensions is hard. What is, okay.
Yes. Depth, yeah.
Yeah, depth.
Yeah.
Fourth dimension is what?
The fourth dimension would be time, but we're not going to talk about that.
Wait, I thought four-dimensional was also like third dimension. Like the Star Wars ride at Disneyland when we're like sitting and then it like moves around too. Isn't that?
Oh yes. The fourth dimension is vibration. And the fifth dimension is when they spray water on you. All right, so that's the S. The p orbitals, ladies and gentlemen, are the second shape of orbitals, and the p orbitals are a little bit higher in energy than the s orbitals. Oh well, win some, you lose some, I guess. So this is the shape of the p orbital. Fair enough, yeah. It's a three-dimensional infinity. It's like a dumbbell shape. So the p orbital is kind of dumbbell shaped, and there's two lobes, and the electrons can cruise around between whatever lobe they want. And the p orbitals can be rotated in space. So this is called the px, x-axis. This is called the py, y-axis. And this is the pz, z-axis. So can you see that in your mind's eye, that you can have a px, a py, or a pz? So in the p orbitals, there are three different types of p orbitals: the x, the y, and the z. How many electrons go in each orbital? 2, exactly. No matter what kind of orbital it is, no matter how high the energy is, each orbital can only hold 2. So normally, 2 electrons per orbital multiplied by 3 orbital types, the p can hold how many electrons?
6.
The 6. Good. So the p orbitals can hold 6, oriented with the x-axis, the y-axis, or the z-axis. So some properties of the p. It's higher in energy than the s. And again, it holds 6. So when the p gets filled, we say p6. All right, so we have S2, P6. Now the d orbitals. The d orbitals are next. But before we talk about the d orbitals, I want to show you something really, really cool. Now we played Battleship when we learned the elements. We played Element Battleship, and you told me that you've played Battleship before. Anyone ever played, like, I mean, we played Bingo too. Remember Bingo? Well, if you play normal Bingo, they say like B7, and you're like, okay, B7, and you're like I15, I15. That's how you find the address of an electron. It's like reading a grid. All right, so here we go. Lithium and beryllium, and sodium and magnesium, and potassium and calcium are in a column that is 2 atoms wide. This column is the S block. Not coincidentally, because the S can hold 2 electrons. Wow. Do you want me to say that again? Yeah. Okay. This column is the S block, because the last electron of these atoms is in the S orbital. It's too wide because the S can hold 2 electrons. This rectangle over here, from boron to neon to unioctium, I'm going to pretend that doesn't exist. From boron to neon to radon to thallium, this rectangle is how wide?
6.
It's 6 wide. Guess what? The last electron of these atoms is where? In the p block, because the p block is 6 atoms across. This is the d block. Count how many atoms across the d block is.
10.
Yep, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Guess how many electrons fit into the d orbitals?
11.
10. And if each orbital can hold 2 electrons, how many d orbitals are there? 5. Yeah, math. So I'm never going to ask you to memorize the locations or the shapes of the D. Don't worry about that. You do need to know the shape of the S and the P, but you don't have to worry about the D's and the F's.
One looks different from the others. All the one at the bottom in the middle. It's got like 2, and then there's a ring around it.
When you become, when you take college level chemistry at your junior year, you'll learn that. I forgot it.
Wow.
Yeah. So when you, it's because it has to do with something called quantum tunneling and the Schrodinger wave equation. I forgot why it looks that way. Yeah. But when you take P-Chem, your junior level and your junior year in chemistry.
Do I have to take that class?
Yeah.
Only if you want to be awesome.
Wait, do you mean junior
So only
year
if
in
I
college?
Yeah.
If I want to become a
okay.
nuclear
I thought you meant
engineer, I
next
need to
year
know
as you
that.
watch.
You'll learn it, but then like me, you'll forget it. You'll learn it, take a test, and then forget it.
That's like playing
You'll take a test and then you'll forget.
I suppose it's entirely possible that there are 6 people in the world that care about that, but I'm not one of them. So, whoops. So D are higher in energy and orbitals than the P, and again we say D10 because the D block orbitals can hold 10 electrons. If we fill them up, we'll have a D10. And if you think those look goofy, wait till you see the next group of orbitals. The F block, yeah.
Bend my suffering.
Is the F block the rare earth metals?
Exactly right, yeah. The F block is rare earth metals. So if you look back behind Rome, you'll see the F block. This is our rare earth block over here. So from lanthanum down to ytterbium, down to nobelium, over to actinium. So look how wide the rare earth block is. 14. So you're going to take Lane's word for it? It's 14? It's 14. So, okay. So if there are 14 atoms in the F block, and each orbital can hold 2 electrons, how many orbitals does the F have? Go the other direction. 7, yeah, okay. And look how cool these guys look with the little loopies here and the crazy lobes. And so anyway, so all you really need to know about the Fs is there are 7 of them, and they're very high in energy.
No, I really don't like that.
Well, you don't have to memorize what they look like. You just have to know that there are 7 of them.
7 is not a good number. Exactly. I live in Vegas.
Okay, guys, I need to be able to hear the question in the back. Okay, ladies.
The total of all the electrons is like the total of the orbit they're in.
Yep. When you look at an atom's final electron, you're going to be able to sum up the S's, the P's, and the D's, and you add them all up, and that's going to be the atomic number or the number of electrons. And we're going to do that. But before we do, we have to learn some rules. I got to show you the ASAP science video about how to properly take notes.
Yes.
Yeah. So again, the best way to take notes is read, listen, write down in your own words. If you're just copying it down verbatim, yeah, you're not actually learning. You're just be like, I'm just thinking about writing stuff down. But if you're like, oh, F orbitals, highest in energy, there are 7, I would write F orbitals, highest energy, there are 7. Or write F, highest E, 7 O's, or something. You're not sketching these, are you? Good, okay. Let's move on. So we got blocks of the periodic table. What do you want to call the lithium-magnesium block?
The lithium-magnesium block.
Let's call it the S block. Yeah, that's a good idea. What do you want to call the scandium to zinc block?
D.
The D block, yeah. What do you want to call the boron, neon, radon block? The P block. Okay, good. So elements that are found in the S block have their last electron in an S orbital. Elements in the S block have the last electron in the S orbital. I'm going to walk you through that here in about 30 seconds. Elements in the P block have their last electron in a P orbital. Elements in the D block, you get the idea. Okay, follow the little green dot. Right here. There's sodium. Sodium is 3 levels down in the S block, and it's only